We're going to talk about the odds evens game one more time. Remember, in this game we have player 1 who picks a row. In this case, the rows are either one finger or two finger, and we have player 2 who picks a column, again either one finger or two fingers. But now we've changed the payout slightly from our previous version. In this case, if they're evens, if the numbers are the same, again, player 2 wins, but a different amount. If they're both ones, then player 2 will win 2 units. That's why we have a payoff here of -2. That represents player 2 wins 2 units, $2, say. If they're both 2s, player 2 wins $9. If they're different, a 1 and a 2, or a 2 and a 1, here we have a $5 win for player 1, either way. Who has the advantage in this game, and how should the players play? We've already seen a pure strategy is probably not a good idea. To repeat why, it's clear that if player 1 plays a pure strategy of playing one finger, it's easy for player 2 to take advantage of that and always play one finger and win $2 each time. Or if player 1 plays a pure strategy of playing playing two fingers, player 2 would definitely want to play two fingers as well and win $9. So a pure strategy is one that can be taken advantage of here if player 1 plays that. And similarly, it's clear that if player 2 plays a pure strategy, player 1 can take advantage and guarantee a payment of $5. But what if player 1 picks a mixed strategy? Well, here there are these different payouts. If player 1, for example, picks 1 half the time and 2 half the time, then if player 2 picks 2 fingers, for example, player 2 will pay out $5 half the time and win $9 half the time. That's an average of 5 halves minus 9 halves, which is -4 halves. That's a $2 win on average for player 2. If player 2 picks column 1, picks one finger, which is column 1, then player 2 will win $2 half the time and pay out $5 half the time for an average payout to player 1 of $1.50. So player 2 would, if player 2 knows that player 1 is playing a mixed strategy of half the time one finger and half the time two fingers, player 2 would have an incentive to just play two fingers all the time and win on average $2 per play. But is there a better mixed strategy for player 1 than half the time playing 1 and half the time playing 2? Let's see. What if player 1 picks row 1 with a probability P, and row 2 then with the probability 1 minus P, since it has to be either row 1 or row 2. And when I say row 1 and row 2, again, that's one finger or two fingers in this game. Well, what is the expected return? Well, we'll ask, what is one's expected return if player 2 plays column 1? So let's go here in the column 1 situation. In column 1, the expected return is -2 times P, because one finger is played with probability P, and then we'll add to that 5 times the probability for two fingers, which is 1 minus P. And when we add these together, we get 5, and here we have -2P and -5P, so we have -7P. Well, what is the expected return if player 2 chooses column 2, namely two fingers? Well, then player 2 pays out 5 with probability P and wins 9, so we have -9 times probability 1 minus P. And that's just equal to 5P, and then we have plus 9P, which is 14P minus 9. So we have these different expected returns if player 2 picks column 1 or column 2. Let's look at what we call an equalizing strategy for player 1. If player one picks a value of p that makes these two equal, we'll call that the equalizing strategy. And is it easy to figure out what that is? We just set these two equal to each other. We solve for p in the equation 5 minus 7p equals 14p minus 9. That can easily be written as, moving this over there, we get the 21p equals 14. Or in other words, p is equal to 14 over 21, which is 2/3. So, the equalizing strategy for player one is to use p equal 2/3. Play one finger 2/3 of the time and play two fingers 1/3 of the time. If player one does that, then no matter what, the expected return, whether player two plays one finger or two fingers, the expected return is the same. It'll be 5 minus 7p or 14p minus 9. They'll be the same. What will they be? Well, the expected return will be 5 minus 7 times 2/3, which is 15/3 minus 14/3, which is 1/3. You could have also plugged in p equals 1/3 here, and you get 14/3. 14 times 2/3, which is 28/3, minus 9, which is 27/3, and again you'd get 1/3. P was chosen to make these two equal. So what happens with this equalizing strategy? Player one actually can win, on average, 1/3 of a dollar per play. That doesn't mean on any given play, player one will win 1/3. In fact, player one can't win exactly a third. Player one will either win 5 or lose 2 or lose 9. But on average, player one with this strategy will win 1/3 no matter what player two does. Let's look at things from player two's perspective. Again, here's player one, here's player two. This represents one finger and two fingers, 1 and 2 fingers there for the columns. What happens if player two chooses a mixed strategy, say picking one finger, that's column 1, with probability q, and two fingers, that's column 2, with probability 1 minus q? Well, what's 2's expected return if player 1 plays column 1? In this situation, the expected return will equal, let's see, if player 1 plays, I should have said player 1 plays row 1. These are all wrong. And this should be row 2. If player 1 plays row 1, that's one finger, the expected return is minus 2 times q, because one finger is played by player 2 with probability q, plus 5 times 1 minus q. That simplifies easily to 5 minus 7q. And what about if player 1 plays row 2? Well, then the expected return here is just going to be 5 times q minus 9 times 1 minus q. And that's easily seen to be, 14q minus 9. And again, we can compute player 2's equalizing strategy, which is to set these equal to each other. We solve for q when we write 5 minus 7q equals 14q minus 9. That easily becomes 21q equals 14, just like before, and q equals 2/3. And 1 minus q then will be 1/3. And it's easy to see that in this situation, that expected return is just 5 minus 7 times 2/3, which again here will be 1/3. Remember that 1/3 represents a payout from player 2 to player 1 of 1/3 of a dollar. You'll get the same number here, plugging in q equals 2/3. So ignoring what player 1 does, if player 2 plays the equalizing strategy, which again has q equals 2/3, player 2 plays one finger 2/3 of the time and two fingers 1/3 of the time, then no matter what player 1 does, the average return will be 1/3 of a dollar to player one. So what we've seen with both of these computations is that player one, using his or her equalizing strategy, can guarantee a return of exactly 1/3 of a dollar, no matter what player two does. Player two, using his or her equalizing strategy, can guarantee an expected return of 1/3 of a dollar, meaning pay player one 1/3 of a dollar, no matter what player one does. Each player can force this amount as an expected return. It's because of that that we define the value of the game in this minimax theorem. The minimax theorem says the following thing: if you have any two-person zero-sum game, and it should be a finite game. What do we mean by a finite game? That means we have only a finite number of choices for player one and for player two. X and Y are finite sets, and when that's the case, A can be represented as just a finite m by n matrix. Then there's some number v that we'll call the value of the game. And what does it mean to be the value of a game? It means there's some mixed strategy for player one, so that player one's average gain will be at least this value v, no matter what player two does. And on the flip side, there's some mixed strategy for player two that guarantees that player two's average loss, meaning payout to player one, is at most v, no matter what player one does. We saw in the previous page that for this version of the evens and odds game, with the payouts that we had chosen, the value of the game was exactly 1/3. Each player could play a particular mixed strategy. In this case, they were both the same, with 2/3 of the time choosing finger one and 1/3 of the time choosing finger two, such that for player one could guarantee that as an expected return, and player two, playing player two's mixed strategy, could guarantee the expected return also of that same amount, v, which was 1/3.